Okay, so here's some stuff on section 2.5. So this is about continuity. And the first question is sort of intuitive, and so I'll tell you more formally what continuity means in a second, but when you're looking at a graph, continuity, roughly speaking, means that I can draw the graph without lifting up my pen. So for example, if I start here, I can draw all the way up to x equals -3, but then I would have to lift up my pen and go over here and keep drawing. And by the way, I would count this as having to lift my pen, because I reach this point and I mean, I can't just draw right through because this point isn't actually supposed to be a point. So I count this as not being continuous. Yeah, so it's probably pretty clear where the discontinuities of this function are. Um, for each one, we're gonna, well, yeah, we have to characterize them, but maybe I'll just list all the values of x first. So it looks like it happens here at x equals -3, -2, -1. Nothing really happens at 0. But at 1, I would have to lift my pen to get from here to here. And then at 2, and then it looks like nothing really happens at 3. So -3, -2, -1, 1, and 2. Okay. So let's talk about continuity from the left and the right. This is an example that's continuous from the left, because if I'm drawing from left to right, I'm approaching -3 from the left. There is a point right here. This would not be continuous from the right, because if I'm tracing it this way, it doesn't go anywhere. This is just a hole, or there's no point here. So this is continuous from the left. And yeah, sorry, I shouldn't have used the word hole a second ago, because we're going to use the word hole for something else. I would call this a jump discontinuity, because I mean, my pen has to sort of jump from here to here in order to keep drawing. More formally, a jump discontinuity is when it's you have a different, you approach a different point. If you're approaching from the left, I approach this point. If I'm approaching from the right, I approach this point, and those are different. So that's what we call a jump discontinuity. By the way, well, no, it's not time to make this comment yet. Okay, I'll keep going. -2. This is what we call a hole. This is when it is not continuous from the left or the right, because if I approach -2 from the left, I'm coming up to here and there's no point there. If I'm approaching from the right, I'm also coming to the same point and there's no point there. So this is neither continuous from the left nor the right. And we would call this a hole just because, right, all that's missing is one point here. In fact, if I could just fill this point in, then it would be continuous. For that reason, and now it's time to make this comment, for that reason, these, whoops, video got a little bit blurry, but for that reason, these holes, we also call them removable discontinuities. Removable because I could remove the discontinuity just by filling in the dot. It's like a very small change I could make, and then suddenly the function would be continuous there. So that's a hole, also known as a removable discontinuity. Let's look at -1. This looks like another jump. If I have to draw this, have to jump my pen from here to here. So jump. Is it continuous from the left or the right? Well, this time if I approach from the left, there's nothing there. There's no point there. So it's not continuous from the left, but it is continuous from the right, because if I'm approaching from the right, I go here, and there is a point here. Whoops. Yeah, sorry, you couldn't see that. There is a point up here. So this is continuous from the right. What about at 1? At 1, this is probably what you already know as a vertical asymptote. A vertical asymptote is when from either side, it could be approaching infinity or negative infinity. So if you see this going on, and in particular, if I approach 1 from the left, I find myself going up and up and up to positive infinity. Of course, if I approach 1 from the right, I'm just going here, which is not positive infinity or negative infinity. But the point is, if there's any infinity going on at all, positive infinity or negative infinity, whether it's approaching from the left or from the right, it doesn't matter. We call it a vertical asymptote. This couldn't possibly be continuous from the left, because from the left, the limit is just infinity, and in order to be continuous from the left, there has to be a point there, but there can't be a point at infinity, because infinity is not a real number. So this is definitely not continuous from the left. From the right, though, it is continuous. As I approach the right, I'm approaching here, and this is a filled-in dot. So right. And then let's do 2. 2 would be another jump discontinuity. But let's talk about it more specifically. To really draw the graph, if I'm just sort of sweeping from left to right, I would go up to this point, and then I would have to jump up here and just make a single point right there. And then I would immediately have to jump down here and keep drawing. So I would still call that a jump, but this is another example where I'm going to say that this is not continuous from the left, because from the left I'm coming up to this point and there's nothing there. It's also not continuous from the right, because from the right I'm approaching this point and there's nothing there. There is a point up here, but there's kind of nothing around that point. There's nothing approaching that point. So let's say that's neither. Okay, good. So here is a more formal definition of continuity. F is continuous at a point A if the limit as x goes to a of f of x is just f of a. We've seen a lot of functions like this. The functions where you can get the limit just by plugging in the value of x. And that's what this is saying. X is going to a, and the answer that you get is whatever answer you get by plugging in a. It's just f of a. By the way, we say it's continuous from the right if you do a limit as x goes to a from the right, and that's f of a. And we say continuous from the left if you do the limit from the left, and that's f of a. So like I was saying, we've seen a lot of examples of continuous functions. In fact, I told you about elementary functions, which is all functions that can be built from trigonometrics, exponentials, and inverse trig, and log, and polynomials, and square roots, and basically all of these functions that we know. One noteworthy type of function that is not elementary is a piecewise function, like this. But other than that, basically all of the functions that you know and the functions that have names are elementary functions. and they are all continuous on their domains. Anyway, let's talk about this example. So piecewise functions are interesting because they are not automatically continuous, because they aren't necessarily elementary functions. So here we have a piecewise function. It has this formula for values of x that are different from 3, and then this formula when x equals 3. And the question is this continuous at x equals 3? So how do we check this? Well, let's find the limit as x goes to 3 of f of x. If that gives me the same answer as f of 3, then it is continuous, and otherwise it's not. So how do I find this limit? When I'm doing a limit as x goes to 3, I'm assuming that I'm dealing with values of x that are not exactly equal to 3. That they are close to 3, but they're not exactly equal to 3. Therefore, I can use this formula. This is the formula that you use for values of x that aren't exactly equal to 3. So that's the same thing. Now I just need to do this limit. Of course, the first thing I should check is whether I can just plug in x equals 3. And I see that I can't right away. I'm going to get 0 on the bottom. So actually, since I'm making this comment, I should probably also check whether I'm getting 0 on the top. I am getting 0 on the top. I would get 9 minus 6 minus 3. And when you're getting 0 on the top and the bottom, that means that you should factor and cancel. This one is this, and of course this one is this. I cancel, and now look, my problems are all gone. If I plug in x equals 3, I have no problem. This would be 4 over 6, so 2/3. Okay, great, but I am not done. I still have to answer the question. The limit as x goes to 3 is 2/3. But if I just plug in 3 to the function, now I use this formula. F of 3 would just be 10. In other words, the limit as x goes to 3 did not match f of 3. So no, this is not continuous. But if you notice, there was a a follow-up question. If the answer is no, if it's not continuous, can you redefine f of 3 so that it is continuous? And this is called removing the discontinuity. The answer is yes, because basically it's just because this had a limit. If you remember, if you go back to what we just said, we said that this isn't continuous because the limit of 2/3 didn't match up with f of 3. But we could just make it match up. Like if I just went into this formula and if I crossed off this 10 and I wrote 2/3 there, then that 2/3 would match the limit that we got. So that's all we're going to say. We can remove the discontinuity. Oops, my handwriting gets really bad when I'm writing on camera. By letting f of 3 be 2/3. Okay, good. Couple more examples involving continuity of piecewise functions. Here's a piecewise function, and let's just find all values of x where it's discontinuous. And then for each value where it's discontinuous, we'll state whether it's continuous from the left or the right or neither. What you want to look at for these is what I call these breaking points. Like you're going to, there's certain values of x where you transition from one formula to another. In this scenario, I would say the only breaking point is x equals 1. We use one formula for all values of x less than or equal to 1, and then suddenly after 1, we use this other formula. So really, the only things to check are of course, you can check this function individually. This is just a polynomial, so this would be continuous everywhere. This is also a polynomial, so this would be continuous everywhere. So the only possibility is these breaking points, or x equals 1, because that's the only breaking point. Since I'm using a different formula for values smaller than 1 and larger than 1, I'm going to separate this into a left limit and a right limit. The limit as x goes to 1 from the left of f of x well, for values of x that are smaller than 1, because I'm doing it from the left, if x is smaller than 1, then I use this formula. So I'm going to use x squared plus 1. And now that I know that, and I know that x is going to 1, now I can just plug it in. This is an elementary function. So I've got 2. Meanwhile, if I do the limit as x goes to 1 from the right, what formula should I use? Well, I should use the formula for values of x that are bigger than 1. If x is going to 1 from the right, that means x is bigger than 1. So I use this. And now this limit is easy to find. I just plug in 1. Yeah. So, what happened? In order to be continuous, if I can, in order to be continuous, the limit as x goes to a of f of x has to equal f of a. In the scenario we're in, the limit as x goes to 1 does not exist because the limit from the left and the limit from the right aren't the same. We got 0 in one place and 2 in the other place. So since the left and right limits don't agree, I would say the limit does not exist. So it can't be continuous. And there was a follow-up question that for any value of x that we find, we state whether it's continuous from the left or the right or neither. Luckily, since I'm running out of space, that should be easy to answer. So what is f of 1? F of 1 would be, because this is the rule for all values of x less than or equal to 1, so x equals 1 would fall into this category. So I would use this formula. So f of 1 would just be 2. And that answer matches with the left limit, but not the right limit. So f is continuous from the left. All right. One more here. Find the value of c such that this function is continuous for all x. So the logic behind this is going to be similar. The value of x we should pay attention to is x equals 2. That's the only place where this might not be continuous. And I'm going to do the limit as x goes to 2 from the left. Which of course means I use this formula. As x goes to 2 from the left, I would get 2c plus 1. Meanwhile, if I do the limit as x goes to 2 from the right, what formula should I use? Well, I should use this one. This is for values of x that are bigger than 2. So I write x minus c, and as x goes to 2, so this would be 2 minus c. And in order to be continuous, the left limit and the right limit need to equal each other. So I'm going to set this equal to this. Yeah, and I solve this, so 3c plus 1 equals 2, 3c equals 1, c equals 1/3. Okay, so yeah, I think this is probably about it for section 2.5.